Good morning. I'm Jaewon Shin, Associate Administrator for Aeronautics at NASA headquarters. I'd like to welcome all of you in this auditorium and also on the net to another exciting aeronautics technical seminar this morning. We have a very distinguished speaker and my friend to discuss intelligent control architectures currently under study and development at NASA. Dr. Kalmanze Krishna Kumar, as I call him Krishna, so I'll refer him and call him Krishna, is the leader of the Adaptive Control and Evolvable Systems Group of the Intelligent Systems Division at NASA Ames Research Center. He currently also serves as the principal investigator for the Integrated Resilient Aircraft Control Project within ARMD of the safety program. He joined NASA in June of 2001, and before that he was an associate professor and interim head of aerospace engineering and the director of the Intelligent Control Laboratory at the University of Alabama, Tuscaloosa. Busy guy back then. And I think he's even busier at NASA now. There he gained 12 years of applied and theoretical expertise in automation, modeling, intelligent systems, computing, control, and simulation. And he managed 12 different projects, including data mining, using artificial immune systems for tactics, optimization, autonomous control for space, and artificial intelligence applications for space shuttle anomaly detection. So clearly his field of expertise ranges from aeronautics and space and has all applications. He's been very active in professional society as well. Has several publications in international journals, books, and conference proceedings in the subject of intelligent control. He is the past associate editor of the AIAA Journal of Guidance, Control, and Dynamics, and also past member of AIAA Journal of Aircraft editorial board, and a past chairman of AIAA Technical Committee on Intelligent Systems. He's an associate fellow of AIAA and a recipient of NASA Exceptional Service Medal. Also, Krishna holds a Bachelor of Technology in Aerospace Engineering from Indian Institute of Technology, and he received his doctorate in Electrical and Aerospace Engineering from the University of Alabama. So we look forward to your excellent seminar today. Would you come up and join us?
Okay, good morning everyone. Thanks to Dr. Chen for a nice introduction there. Can we have the first slide, please? So my talk today is going to be on intelligent flight control. The title says toward intelligent flight control, mainly because we have many topics being researched, and also the concept of intelligence itself is a moving target. So we are getting there, and I'll show you where we are in time and talk about some future ideas. I am the principal investigator of resilient aircraft control, which is under safety, but I'll also talk a little bit about applications for next-gen designs and areas that's outside of safety. Intelligent flight control obviously is applicable beyond just safety, but safety, it has one of the big roles, and ARMD is investigating quite a bit that role it can play in safety. Next slide, please. I would like to acknowledge at this point all the researchers that have worked on this and the partners. I would say this research dates back almost 10 years or more. Currently, I think the two projects that are funding some of this research is the resilient aircraft control and the subsonic fixed wing. under the ARMD projects. In the past, we have had many projects that have looked at many pieces that I'll be presenting today. I want to thank all the members of that set of projects that worked on it. And finally, of course, to headquarters for one, giving me this opportunity to come here today, but also supporting and realizing the need for intelligent flight control. Next, please. So my presentation will essentially be kind of three parts. The first part, I will talk about what is intelligent control. As I know today, I say I because it is an active field of research. Every day there's some new ideas being pursued. So this is what I know. The second stream will be looking at applications. I have avoided going through details of these applications. Most of them will be architectures that I will present. And people who have enough control background will realize these architectures kind of look similar, but in a more compact sense, different. We will look at safety and NextGen as our main focus. And finally, some exciting ideas in intelligent control as an enabler for what we call polymorphic control. I'll talk about brain-like intelligent control, where I personally would like to see intelligent control go, and also talk about plug-and-play control architectures. Next, please. So first, I will talk about intelligent control. Next. Okay, so if you look at intelligent control, the concepts in control are very old, maybe 400, 500 centuries old. But the ideas that intelligence is drawn from is relatively new, starting with artificial intelligence. Artificial intelligence as an idea is about 50 years old. And it has taken many elements of cognitive science, psychology, philosophy, and so on. And of course, computer science came along to boost its applicability to many different current engineering systems. And that gave birth to this idea of intelligent systems. So many folks will consider intelligent system as a kind of a rational artificial intelligence, trying to make machines perform better than what they are capable of. Some of the ideas in intelligent systems that are new and not so much in traditional AI is the idea of biological systems, looking at biology as an inspiration, also modeling abilities. Software and hardware revolution that's taken place that's made implementing some of these very complex algorithms much easier. And finally, intelligent control, like I said, does have traditional control features such as robust control, optimal control, but also has brought in some of the new ideas in predictive, adaptive, real-time optimal, and learning and planning down to an implementable level in hardware and in real systems. Next, please. AI, like I said, is quite old compared to intelligent control. It's evolved into two areas. One is looking at humanistic AI, trying to model human and understand how humans think and behave. But the one that is closer to an engineering application is the rationalistic AI that is using what we know about intelligence to do the right thing from a machine point of view. Next, please. The quote I like that's shown at the bottom that's more relevant to intelligent systems is the branch of computer science that's concerned with the automation of intelligent behavior. So how do you automate the intelligent behavior as we know it to make the machines better than what they are? Next, please. So towards, using this as a foundation here, I think of intelligent control is an objective to achieve intelligent behavior that enables higher degrees of autonomy. So I have a little architecture here that I use to highlight what I mean by towards higher degrees of autonomy. This architecture is out of safety. It's a good way to illustrate higher degrees of autonomy. We do have a pilot in the loop, and the airplane suffers some kind of a damage or an offset condition. A typical current generation airplanes, the pilot will have to adapt to that condition. And sometimes the time frames can be quite small, down to almost a second type adaptation. So the pilot has to work harder, and in addition to that, he has to manage his resources. So there is quite a bit of workload on the pilot. Now, when intelligent control comes in, is the first thing it can do is adapt to the damage, provide stability. Stability is one of the events that needs to happen down to sub-second levels. And that takes away some workload right away. So that's 1 degree higher autonomy. Pilot is not really directly controlling that aspect of it. The next level of autonomy is once the airplane is stabilized, we still have to bring it down and land it safely. So there are many little pieces that needs to happen. One of them is a trajectory planning. Now that I have a reduced envelope after the damage, the aircraft needs to figure out what it has and come up with a plan that will safely land the aircraft. So here is another level of autonomy that's provided to the pilot, and the pilot can then opt to either use it or not use it. And that's the idea of having that variable autonomy as an option to the pilot. So intelligent control, once again, I think of it, the objective is to achieve intelligent behavior that enables higher degrees of autonomy. This may be more relevant to aircraft as a definition, but that's the field that I work in, so it fits well. I will also show you, can you go to the next slide, please? There are other ways to quickly define intelligent control. I'll show you a couple of ways you could do it. These are the ways I've used to communicate. I don't know if you can see the red color there, but if you look at controlling any system, we need 2 error signals. We need to get an error signal that shows you what is the difference between desired and the output of the system. So sometimes even the desired is not clear. That's where the goals come in, the planning comes in, and even their intelligence can play a role. And once we know what we want to achieve, how do we get that in control? What is the error in the control activity? So that's another signal. So intelligent control can be thought of as a way to generate these signals to achieve higher intelligence. Can you move to the next slide, please? Another way I've used to define intelligent control using typical levels that you might have seen in many areas where it's easier to show in a hierarchy of sophistication. So here at level 0, I think of it as robust control, which is kind of an instantaneous gain feedback controller. At level 1, you are now adjusting the gains of the feedback to get better adaptation to the current situation. And from level 1 onwards, it's almost happening in real time. That is, it is happening online, it's an error correction, optimality, planning, and so on. So this level you can keep going further down the level or higher up the level to achieve higher intelligence. We have used this hierarchy when we guide our research in intelligent flight control. Next, please. Some of the desired characteristics of intelligent control based on what we know today is the decision making under uncertainty, fault tolerance, learning and adaptation. The 4th bullet is a very interesting concept. It's playing a bigger and bigger role, which is where I think towards the end of the presentation I'll talk about brain-like intelligent control. That's where we want to go, which is real-time and long-term performance optimization. Can I optimize as I'm flying? These are very applicable to even space travel, for example, where if you have onboard capability to sense the trajectory, then you can do long-term optimization. And finally, extrapolated reasoning. Next, please. So some of the capabilities we are after, autonomy enabler, I already mentioned that. Damage adaptive control. The 3rd bullet there, data rich, model poor. I think there is clearly, you will see more and more, sensing is sometimes easier than physically modeling an event. Mainly because the physics is either quite complex or the computing power that you need to model that physics may not be available for real-time applications, for example. So sometimes it may be easy to sense and control based on what we sense, similar to what biological systems do. And intelligent control as capability, it's got that aspect to it. Rapid prototyping and reduced development cost. I can say from my experience, I can go from one aircraft to another aircraft, completely different classes of aircraft, and I can design an adaptive intelligent control in matter of days. So that kind of a quick prototyping is possible. Improved stability margins, that's one of the aspects of safety that we are looking after or we are going after. And I'll talk about plug and play and reusability. Next slide, please. Okay, hopefully that gave a feel for what is intelligent control and what we are trying to achieve in terms of capabilities using intelligent control. Next, please. So next few slides, I will talk about applications to aviation safety and next-gen designs. Next, please. So if you look at safety, aviation safety, of course, has many requirements. Control is one piece of that solution. But in terms of control, what are we seeking? Our capabilities we are looking for is, if one word I have to say it is safe landing. Kind of bring it down and land it safely. But to achieve that, we need to first understand stability, because that's the first thing that needs to happen. I should be able to recover from loss of control, in the sense, understand how to maneuver the aircraft, and at the same time provide handling qualities that are consistent with what the pilot expects, so that there is no confusion while doing all of this to the pilot. Next, please. Motivation is simple. I have shown 3 pictures here, but you can get many pictures out of the web of incidents and accidents that have led to the desire to help the pilot. These are, fortunately, 2 of these, the pilots have survived and brought down the aircraft quite well, because they had the time and they had the experience to do it. The third one, the tail damage one, did not survive. The essence here is to understand that pilots who are trained can bring down most of these incidents, but there is no real ability to train for all types of incidents that might happen. And the other aspect to safety is that many of these aircraft are built with redundant controllability, and we want to exploit that. So hopefully in the next few slides, I will highlight how we can exploit that. Next slide, please. Okay, here is an example scenario. I know you cannot read that 1 through 6, but I will take you through. So there is an event, that's 1, that takes place. First thing you do is number 2, which is stabilize the vehicle. Number 3 is you perform a quick assessment of what is available. So this is similar to what you may do if you get hurt, for example. The first thing is you isolate. You don't want to use that arm because something went wrong. That's the first thing you do. That's similar to stabilizing. The second thing you do is assessment. What is wrong with it? And the third and number 4 in this is to come up with what we call flyable trajectories. Now this is where the concept of variable autonomy comes, because we have a pilot in the loop. So we want to provide the pilot an option of choosing. So here I've given 2 choices, 5 and 6. Later on I'll show you an actual experimental data where 5 assumes a restricted set of envelope and 6 assumes a little relaxed, a bit higher risk but more flyable trajectory. So the pilot can choose it. Now where does intelligent control come into all of this? So that's where the next few slides will talk about that. Next slide, please. So here is an architecture we are going after in safety. We have several blocks in here. This is a typical control architecture. If you look in the middle, there is adaptive control, which is one of our big focus. How do I provide extra stability? But there are also questions like, can I use the engine as an extra effector? How do I have to design or redesign the engines to provide me an ability to control the moments from a stability and maneuverability point of view, beyond what is available right now? And you see at the big block, which is all of the planning functions. I need to be able to do guidance, emergency planning, trajectory planning, and so on. So next, please. The next few slides, I'll concentrate on adaptive control, next, and also on emergency planning. So those will be my two topics I will talk about. Under Resilient Aircraft Control Project, we are looking all aspects from this architecture. Next, please. So this is one of the popular adaptive control architectures that came out of the research by Dr. Tony Calise at Georgia Tech. It's called the direct adaptive control architecture. It uses a neural network that's in the red block there to adapt to unforeseen events. The beauty of this direct adaptation is you don't need to do system identification. You don't have to spend any time IDing or identifying what has gone wrong with the system. And the benefit of that is it can accommodate many different types of incidents, not just wing damage or tail damage, but any combinations of that. So it has a pre-trained neural net, or if you want to think of it as just a function that captures known dynamics before the fault happens, before the damage happens. So this is the current knowledge of what the system can do. And on the left, you see desired handling qualities. So the pilot, when he interfaces with the airplane through the stick, is actually asking for desired roll rate, pitch rate, yaw rate, and through an expectation model, what we call the handling qualities model, what kind of a short period or the Dutch roll he expects. And typically there is a controller that takes that input, shapes it into control surface deflections that go to the airplane. And on the right, you see the sensing taking place. Now at the bottom, we had those two components, the fixed neural net and an adapting neural net. Neural networks were used because they have their own nice features. I don't have time to go through that, but you can also use any parameterized function instead of neural networks. Now, what we have done so far under the current safety project and previous projects is we have researched this architecture quite a bit. So some of the results I'll show you today include flight test results that were done at NASA Dryden, and some of the simulation work that was done at NASA Ames and Langley. Now, let's move on to the next slide, please. So if you look at the flight test results that were done so far, it uses an F-15 currently available at NASA Dryden. The nice thing about using an F-15, it's immediate to think of F-15 as not being very relevant to transport aircraft, but the beauty of an F-15 is you can take it to the edge and knowing very well that it's got the performance to come back. So you can experiment with the high performance aircraft, all of the features that you're looking for much more safely, since we have pilot in the loop, much more safely than you could with the actual transport aircraft. So the F-15, the modified F-15 that's available at Dryden has two canard surfaces. Those are the two surfaces in the front. Those are scheduled as a function of angle of attack. So we can actually modify that scheduling to create instability in the system. So that's what we did. We took the multiplier that multiplies with angle of attack to the canard surface and messed with it, changed it to make it unstable. And what I'll show you is the video first, and then I'll show you a set of data. In the video, we have basically a short one where you will hear the pilot actually talk through what he's doing. As a quick preview, I would say that the first you will see is flying with no adaptation, in other words, no neural networks. And in the second phase, he's flying with neural networks or with adaptation. And you will see through his commentary what he thinks about the handling qualities. So this video will highlight the handling qualities of the pilot. And then I'll show you a set of data that highlight the stability as control engineers would like to see. So it captures both the pilot in the loop effect of adaptation and the stability. Now I do want to point out there's a temptation to say we could do a lot of this experimentation with unmanned systems, and that's true, we can do a lot of it. But when there is a pilot in the loop, it completely changes everything, because now we are talking about a realm we are getting into where there are two systems adapting, the pilot and the software. So that interaction is poorly understood, and we, through experimentation, we figured out even we don't fully understand it. And pilot-induced oscillation is one of those events that are not desired, and that's the thing we want to avoid when we have both the computer and the pilot adapting. So with that, let's move on to the video, please, and I'll keep quiet through the video.
For failure?
Here comes the failure. Okay, failure's in. Just right at the edge of desired tolerances there, so we made it still. One more, a little bit aggressive. Same thing, right on the edge. I'm overshooting a little bit from where I want to be. Still making desired tolerances. Here comes one aggressive one. Okay, a little bit light in the seat. Here comes the failure. Okay, a little pitch up there. No PIO tendency, and just stopped it right in the middle of the position where I wanted to. Let's do a high to low here. Okay, perfect. That stopped exactly where I wanted it. Let's do one more. Okay, right in there. Actually, it seems like it's better in the going down. Let me try one more from the bottom position. Yeah, stopping it right there. We talked about that. Predictability, it seemed to be much more predictable with the neural networks on. Fine tracking is good. We're keeping it within about 5 mils. I'm happy with that. DV up to the north, or up to the forward. Bring the pipper back on. Okay, easily within side desired.
Okay, so that's the short video. Hopefully you heard pilots say initially a little bit oscillatory with the neural nets off, adaptation off, and with the neural net on, it was right on the money. He asked for a pitch up, it gave him a pitch up. Now, this is one of the things that we are trying to achieve simultaneously with stability is consistent handling qualities. When we have a pilot in the loop, all of these become very critical issues. When we go to unmanned systems, some of these may not be that critical, and still there are challenges with the unmanned systems. Next slide, please. Okay, so this is a busy slide here. I have two busy slides, but I had to have them to communicate the beauty of using adaptation. What you see is a typical control tool that we use to assess stability. This is called Bode plot, and on the top we have the gain margin, and the bottom we have phase margin. We want, of course, gain margins to be good, about 6 dB or more, and about 60 degrees of phase margin. The gain and phase talk about really the sensitivity to modifications to feedback signals and time delays in signals. So the stable region and unstable regions are very well marked there in white. The blue line is the flight data. So we flew several flights at various levels of destabilization, all the way up to neutral stability, which is shown on the right at minus 1.75 Canard multiplier. And the blue symbols on the line is the actual flight test data. Then on the top there is a black line, black dashed lines. Those are the simulation data. So whenever we do our experiment, of course, we first do it in our offices, then in a small engineering simulator, then in a full engineering simulator, and finally in the actual aircraft. So the black line is a full engineering simulation where there is a pilot in the loop, and you can see the simulation does not capture all of the non-linearities that you get out of a flight test. So right there is one selling point for flight testing ideas, because you don't really capture all of the non-linearities that you want to really simulate. Now, in the next slide, I will show you the concept that I've been saying about consistent handling qualities or consistent performance. You will see how when we have a neural net adaptation on, by the way, this is without neural net adaptation. So when I turn the neural net back on, both simulation and flight tests will look very similar. So can we go to the next slide, please? So here is, there are two pieces of information here. One is, by turning the adaptation on, simulation and flight tests behave the same. And the reason for that is the adaptation. It's adapting, making the simulator behave like the real airplane by adapting the handling qualities model, because the neural net is able to absorb all the non-linearities. And the other thing I want to point out here is you can see the best place to see it is at the rightmost. We have gotten back the 6 dB. Before, in the previous slide, we had 0 dB at the extreme right. Now I have minus 6 dB. So by turning the adaptation on, I got back the stability that I was hoping for. So this is something that is a big selling point for adaptation. You can gain back the stability that you lose by having damaged situation. Can you go to the next slide, please? Okay, so we so far talked about the role of adaptive control of providing increased stability. But like I said, stability alone doesn't do it. You have to safely land the airplane, which means I should be able to identify what I have and come up with a plan to bring the airplane down. So towards this, we have been working on some other technology highlighted in red, the adaptive flight planner, for example. It's adaptive in the sense it is constantly and consistently gets envelope constraints fed into it, and it does real-time planning. So typical planning software, for example, the ones used for Mars applications, they are not truly real-time in the sense there are humans on Earth that change the plan based on feedback. But here it's done on the fly. It gets input from the software and changes the plan. The other nice thing about this approach is you can come up with what-if scenarios. So let's go to the next slide, please. So here are two examples. So on the left, we have a 15-degree rudder jam that just happened, and the model estimates that the best I can do is make only right turns. Safest thing is to do, make a right turn, and you can still land at the final landing area that's shown. Or you can relax it a little bit and come up with a better manageable path shown on the right. So the pilot could be given these two options, or maybe 4 or 5 options. And once you are stable, now you have time to react to these options. You can say the right one is, although maybe higher risk, but I think I can do it based on what I know. So these are the trade-offs that you can do in real time, provided to the pilot to safely land the vehicle. Next slide, please. Okay, so here is another very interesting example we looked at. And this is where I'm trying to take to the higher levels of intelligence per se. I have here a C-17 airplane, which most of us know is high performance vehicle. It's such a beautiful vehicle from a control point of view. It's got so many surfaces to play with. You can actually, it's got like 24 control surfaces. So it's like a controller's dream right there. But they are all not used for safety. They are used only for performance, to get the high lift, high drag, tactical descent, for example. So what we said was, let's try to see for a damage scenario how we can use these surfaces. Can you go to the next slide, please? But here is the challenge. It's not straightforward. There are many different surfaces with many different authority. For example, if you look at the roll control authority on the bottom right, you see pretty much you can use any surface to get roll. So how do you do this optimally and in real time? So towards this, we came up with another architecture. Next, please. So here is, I'm adding more pieces to my intelligent flight control. I have 2 more pieces on the top. I don't know if you can read that very well. The one on the right says optimal control allocation, and one on the left says adaptive critic. So let me briefly say what they do. Optimal control allocation basically looks at a performance index and tries to come up with the right set of control surfaces to actuate to give you that performance. In our case, it was simply minimum error, but you could also say minimum drag or minimum noise, whatever you want to choose as your performance. The nice thing is it does that in real time. On the left, we have an adaptive critic. Adaptive critic is based on very classical optimal control theorem called the dynamic programming, the principle of optimality. So what it does is it helps you do real-time optimal reference model adaptation. In C17, we realized very quickly that although it is highly controllable, the reference model, that is the handling qualities model, is unachievable because of the surface constraints we have. So we can actually tone it down a little bit, but how do you do that cleverly? And that's where adaptive critics come. Can you go to the next slide, please? I don't have too many charts. I just have one chart, and I know it looks kind of busy, a little fuzzy too, because this was done like 4 or 5 years ago. But what it shows is we flew several flights in simulation. This shows one of them, and you can see where the aircraft is making a rapid descent. So on the left axis you have the altitude, and on the x-axis you have time to touch, distance to touchdown. So at about 20,000 feet, the stabilator fails, one of the stabilators. And a little later time, elevator fails. And a little later time, the rudder fails. A little later time, aileron fails, and so on. All the way down to one engine failing. So this is all happening on one side of the airplane, the assumption being some kind of a hydraulic leak has taken place and series of failures. Now, what was the beauty was, I don't have a video that captures this, but the pilot really didn't feel a thing because it's highly controllable. So the intelligent flight control figured out the right settings to give him to keep the stability going, and he could land it all the way down. I do have a video that I'll run in a minute that showcases only one thing. It shows a tail failure. By that I mean all the control surfaces in a tail fail. In a typical transport aircraft, that is a disaster. You can no longer have pitch control or yaw control. But here, you'll see that at least from the little video I have, basically nothing changes. The tail fails and you can still fly the airplane. That was the beauty of C-17. Now, one other thing I want to add here is that when we did all of this, we realized very quickly that we did not fully understand the structural constraints. When we do move secondary control surfaces, we don't know what the effect of the aeroelastic behavior will be. So that's one other research area of study that we are pursuing under resilient aircraft control. Can we roll the video, please? Do we have the video? Okay, here we go. So it's a C-17 simulated, it's got its own stability augmentation system engaged under adaptive control, and you have a tail failure, and it pretty much flies. If there is a tail failure at this point, it will dive to the ocean without adaptation because you have no other surfaces to control. So this just, it's a small video. I have lots of other videos, but we thought this would be the best one to show for the time we have. I think it will stop pretty soon. We had about 3 to 4 pilots come and fly the C-17. If you recognize, there's a San Francisco airport being simulated. Okay, we can move to the slides whenever. Okay, thanks. The next slide, please. Okay, so what are the aviation safety challenges? We have plenty of challenges. Number one challenge, of course, is the idea of getting it into the real aircraft or the real fleet of aircraft. For that, we feel there needs to be some metrics. I know stability is a good metric, but adaptive control, being adaptive control, do the traditional metrics like transient steady state, rise time, settle time, and so on, are those sufficient? Do we really understand while adaptation what happens to the actual software? So there are some metrics needed, and we should be able to show that if you define a metric, I can consistently 100% of the time do the same thing for repeatability. So that's where the stability and performance guarantees come. We also have challenges in integrated flight and propulsion control. How do I design the next generation engines that will give you the ability to control yaw, pitch, and roll? Verification and validation is a big problem. Verification, especially since the software is quite complex. How do we do that? I have the last three bullets are more towards how do we flight test this. I have manned, I can use manned system versus unmanned. Unmanned is cheaper, but we don't learn the whole story. We need manned systems and they're expensive. Subscale versus full scale. So there are challenges there. Right now at NASA Langley, we are looking at subscale models that have been balanced. They have the inertia balance, so we can learn a bit more than cheap off-the-shelf subscale models. And finally, can we use the next-gen designs like the blended wing body to look at safety issues? Or is that too much to ask for since they're only conceptual designs? Should we wait for them to be more solid designs before we try it? So there are many challenges when it comes to validation. Next slide, please. Okay, in the next few minutes, I will talk about how intelligent control can play a big role in next-gen designs. We will look at three ideas. The capabilities we are after are listed here: rapid prototyping, database was physics-based, integrated flight and propulsion control, increased autonomy for certain applications, enabler for increased performance. A colleague of mine kept saying it's like the 3M commercials. Like the way they say, we don't do anything, but we do everything better. So you give an airplane, we'll make it fly better. You give an airplane, we make it safer. So intelligent flight control doesn't really directly feed into the design itself. It could, but most of our challenges are once an airplane is given, how do you make it better, more efficient, more safe? And finally, consistent handling qualities. Next slide, please. Okay, so I'll talk about three applications. One is in intelligent engine control. The other one is in the cruise efficient short takeoff and landing. And the last one is in payload-directed flight. Next, please. Okay, here is a challenge that we looked at, which is, I think, very applicable to next-gen as we talk about fuel-efficient engines. Engines are modeled reasonably well, but there are some phenomena that are not modeled because of the physics is so complex. And one of them is the combustion. Combustion is a highly inherently unstable pressure fluctuations and a noisy system. So if you try to run the combustion lean, this instability will blow the flame off, and that's not good. So to keep the flame going, they run it rich, and that is not fuel efficient. So if I can provide stability via control, then I can run it leaner and get better fuel efficiency. But to do that, we don't have good models of the combustor itself. So how do you actually go about coming up with a control algorithm that will work well for such a situation? So here is where another intelligent control approach comes in, called predictive control. At the bottom, you see a set of arrows there. What it's trying to tell you is that if you give me a collection of past outputs and the present output and past inputs, then I can predict the future up to some horizon. So theoretically, given how much you give me in the past, I can predict so much in the future. So once I can predict, I can use that to control the engine for the future. So this is called the predictive optimal control. Can you go to the next slide, please? So here is a simple architecture that we used. There's a red block there. What it is a highly intensive mathematical computation. Lots of matrices and inversion and so on. but out of that comes a control that achieves much better stability. So on the right, for example, you see the pressure fluctuation as a function of time. The blue is a non-adaptive fixed controller because you don't have a good model. But the red one, it takes a little bit of time till the data is accumulated, then it adapts and just completely stabilizes the pressure fluctuations. So that's a good example of how you could use data versus model in areas where it is difficult to come up with models. Next slide, please. The next application is something being pursued right now under subsonic fixed wing project. The cruise efficient short takeoff and landing is a conceptual vehicle. It's got many options in terms of how do you generate the extra lift using engine blowing the air from the engine. And all of these are, the actual physics is being studied in wind tunnels and so on. It is quite an intensive effort to understand the designs from the physics point of view. So one aspect that we thought of was, can I do this without a good physics model? So going back to the same data versus physics. If I can sense what the airplane is doing, can I use that to control with limited physics-based models? Some of the control challenges are listed here. There's a strong engine aerodynamic coupling in ESTOL vehicles. There's plenty of control redundancy. Not all for safety or performance, they're used for simply to provide the extra lift, but can we use that for control? The transition to and from backside of the power curve to the front side, because these cruise efficient short takeoff are meant for smaller runways, which means you have to fly slower as you come down to approach. And how do you achieve that, and how do you provide the safety and performance for that? Next slide, please. So very quickly, this is the architecture we are looking at. Everything that you see red are what we consider intelligent flight control. We have an adaptive inner loop. We have an intelligent control allocator. And we have that big chunk there called the database predictive control, where all of our predictive algorithms will go in to predict the flight since we don't have good models for the aircraft. So we have been working with a couple of industries looking at future next generation designs here and how we can simulate and test these ideas. Next slide, please. This is one of the, I would say, applications for the unmanned systems. Like I said earlier, intelligent control for unmanned systems, you can really think very differently from manned systems. All of a sudden, you can open it up and think of new ideas. So here, the whole concept, I think, can be better explained in the next slide. But before we move on, the dashed line there is the payload-directed flight block. So that's the research. How do we come up with that? So to explain that, let me go to the next slide, please. Okay, here's an example mission. Being from California, I think it's clear that fighting forest fires is one big challenge we have. And right now, manned aircraft help, and also unmanned for surveillance to actually map out that region. But the question is, can this be done with real-time planning and control? That is, can I use an unmanned system that has a sensor on board that can detect fires and actually go to those regions and map it out, and maybe eventually even help with putting out the fire itself? So how do we achieve this kind of intelligence on board? Typical autopilot systems, for example, will have altitude hold or speed hold or a climb or a descent. But here in this application, it may be combinations of them. It may be something where the sensor says, give me a profile, flight profile that will keep constant infrared signal or constant thermal signatures. So as soon as you start speaking sensor language, the interface from the sensor to the actual control on the unmanned aircraft gets complicated. So how do you make that simpler? Can you go to the next slide, please? So we are looking at some of the intelligent flight control concepts here. On the top, you see multiple autopilot modes. They are very different from conventional modes. Instead of altitude hold, we are going to say waypoint hold. You just follow the waypoints. Or we can say contour hold. You can say that I want an image contour, hold that image contour. Or you can say thermal signature hold. So how do you take that kind of a command from the sensor and translate it into control? To be beneficial, it also needs planning and feature extraction as one of the key components of intelligent control. Next slide, please. There are many applications of payload-directed flight. I don't have to say that here. We all know that. Some of the new ideas for airspace applications is in formation flight. Formation flight is shown to reduce drag. So how do you achieve formation flight, keeping two airplanes purely based on the sensor feedback? And also futuristic unmanned cargo aircraft, how do you keep them in profiles that are low noise, non-interfering type trajectories? Next slide, please. Okay, so with that, hopefully I gave a flavor of the research being done at NASA in aviation safety and NextGen. What I want to do in the next 10 minutes I have is talk about some of the future ideas. These are ideas that are, I wouldn't say they're directly funded by anyone, but it's something we as researchers always look for new concepts that we can pursue. So next, please. So I'll highlight three ideas. One is called polymorphic control system. The second one is the brain-like intelligent control, and finally, intelligent plug-and-play control. Next, please. Okay, I just said that. Can we move to the next slide, please? Okay, so what is polymorphic control system? As we started working with intelligent control, we soon realized that there is a potential for helping out multiple unmanned systems. So for example, let's say I have a couple of UAVs flying along and there's a bunch of unmanned ground vehicles that are coordinating a task with the UAVs. Now, how can I share resources across wireless networks? I may be able to use a sensor from a ground vehicle for control on the aerial vehicle. So we built a mathematical architecture using topological formulations for sharing the data across physical boundaries. So all the applications I showed, we were using within the physical boundary. I have an airplane, one actuator fails, I'm using the other actuator. But here I'm going across the boundaries, exploiting the wireless networks, networking capabilities that we have. Next slide, please. So we have looked at two applications. I'll talk about the bottom one because I have a short video of that. So here is an example of how an unmanned aircraft signals saying it has a complete INS failure, which is the inertial navigation system failure. Then a ground vehicle moves into position, identifies the aircraft, and visually tracks it and gives that information back to the airplane and helps it guide it down to landing. So all the sensors on board has failed, and the sensing is coming from an unmanned vehicle that's stationary on the ground. So the video that I'll show you was flown at NASA Ames using a Cessna scale model under rover, and you will see as the aircraft is coming down to land, it's totally unpiloted. It's autonomous, and towards the end you'll see the rover's position as it's watching the aerial vehicle. So here is another example of where intelligent control can play a role across physical boundaries. Can we roll the tape, please? Okay, so that's the UAV. It now signals to the rover that something has gone wrong. It's got a failure. And from now on, the rover actually guides it all the way down to flare and touchdown. I was told that one of the uniqueness of this is it actually flares, as you saw there. Typical autonomous flight down to earth don't flare. They just come. It's a crash, almost a crash landing. So hopefully you got to see the rover as it went by. It's a little rover that was sitting on the side. Okay, so we have done interesting experiments. Again, these are kind of unfunded, so not real good videos here to show you. Can we move to the next slide, please? Okay, so this I think is the kind of the exciting, the future of intelligent control. If you look at the brain statistics, just the numbers of what we have, 10 to the power 13 neurons. That's 1 million trillion number of neurons. And if you assume these connections are storage, part of the storage, we have something like 10 to the power 15 bits of data that we store. Another thing we know about brain characteristics is it's a complex system that works. We know that we do optimization over time. We are always planning ahead. We have emotional or secondary reinforcement. And we have an action corresponding control component. And we also have an expectation system. So the question is, how do you take these concepts and try to build a machine that can move towards brain-like intelligent control? One thing we are going to see right away is that if I'm going to have that much capacity, it has to be modular. So neural networks is one way to do it. I repeat the neurons. I can test one neuron and then say I have billions of neurons working the same way. So verification becomes easier. But I can also capture complex models via learning. So there's no way I can sit and program a 1 trillion memory in a hardware. I have to do online learning. So I have neural networks and online learning, and I have ability to capture the optimization over time, the predictability, and the secondary reinforcement. So can you move to the next slide, please? So here is an architecture in a very simplistic way. Buried under that is a bunch of equations and neural networks. And these have not been proven to do much else. I mean, so far, people are researching that, and we are looking into that too. So what it has is a 3-component box here. So the one on the right in green is a bunch of neural networks that capture the performance over time. And the blue one is the prediction model. So a bunch of neural networks that sits and predicts, models the future times. And then we have a controller. And at the bottom, I've shown you how, in a cartoonish way, how you can adapt the controller online by using some ideas from optimal control. Can you go to the next slide, please? So here is something, if you actually open it up, it may look somewhat like this, that I'm using systems from TF minus delta T to predict TI and down to the current time T and future times. So this can very quickly unravel into something complicated. So what we are looking at are in a very minimal way is how do we come up with, in the simplistic way, maybe a 3-neuron architecture that can do control, prediction, and reinforcement, and then multiply it several million times to get the power of brain-like intelligent control. Some of the applications that we have talked about in the past, for example, low thrust trajectories. If I can have spacecraft self-locate itself instead of using the deep space network, then I can come up with trajectories that are self-correcting itself. And since we are talking about now months of travel, you need to have brain-like intelligent control for long-term optimization and control. So how do we achieve that? Through intelligence or intelligent control. Next slide, please. So the final idea that we have pursued, and I think it's got potential use going into the future, one of the aspects of any complex software is verification. Verification cost is skyrocketing because every line of software adds to verification cost. So there is a desire to do some of this in hardware. So when we say hardware, can I come up with a verified hardware that I can use on any system? So that was the question. Can I take a hardware, a control hardware that works on an airplane and put it on a rover? Will it work? So we took this concept and actually applied it to different systems. Let me show you that next. Can you go next slide, please? So here is conceptually what we can have. On the right side is a platform. On the left side is a hardware. They do a handshake. and pick the right control block to run the controller. Can you go to the next slide, please? Again, this kind of highlights the benefits of going plug-and-play control. We did a study, actually SRS Technologies, I think they're called Mantech Systems now. They did a study for us looking at adaptive control, just adaptive control, how much cost savings there could be. And they found through quantitative study that compared to traditional gain scheduling, you can save 23% of the cost right there for avionics software. So our push is that if you really go down to the repeatable, reconfigurable hardware, then we could save a lot more money, and mainly from software development, but also in verification costs. Next slide, please. So I'll show you very quickly 4 applications, and the only thing I'm trying to motivate here is the architecture really doesn't change much. When I go from an aircraft to an unmanned aircraft to a ground vehicle to a space application. So it is there. I mean, we have the tools there. We just have to make it happen. Can you go, please? Next slide, please. Okay, so here is concentrate on the IPNPC block there. It looks the same from this slide to the next slide to the next slide. Next slide, please. And these are all examples that we actually did. So these are not just conceptual architectures, but we actually have used this. So here is one for unmanned application for, we were looking at a Mars application at that time. And we can use the same architecture, the inner loop. The outer box has changed. So the majority of that stays the same. Next slide, please. And we use that for a rover control. We showed steering control, you can do that. Next slide, please. And we did that for docking. So we showed 4 very different classes of applications, and showed that you can have plug-and-play capability in the areas that we have looked at. Next slide, please. Okay, so this brings me to the last slide of the talk. Hopefully I gave you a flavor of what we are pursuing under aeronautics from safety and next-gen point of view, and also some of the ideas that are out there, future ideas that we are getting into in a small way to understand the capabilities of intelligent flight control. But we do have a lot more challenges. I listed them here. Some are obvious, for example, control objectives. Yeah, we have to worry about stability. How do you quantify stability, transient performance, and so on? What do you mean by autonomy, from a full autonomy to variable autonomy? What role do they play? There have been lots of talk about bio-inspired systems. Bio-inspired systems are good in many ways, but they bring their own challenges. Sometimes I feel they may be a little distraction. Just because it works well in biology, that doesn't mean it's going to be the right solution for us. So that's a challenge when people come up with new ideas that are bio-inspired. I think software V&V is a big puzzle. That may be one of the things that we might have difficulty overcoming unless we spend a lot of research dollars. I know that it's a big topic, top of the agenda for National Science Foundation and for many other research labs. And finally, brain-like intelligent control is an open research issue, lots to be done there. And I think a lot of benefits will come out of that. With that, next slide, please. Open it up for questions. I took this quote from Einstein, and I think it kind of reads funny, but it's got a lot of meaning to it. If we really knew what we were doing, somebody will be selling it, right? So, okay, that's all I have.
Good afternoon. I'm Beth Dickey with NASA Headquarters Public Affairs, and I'll be moderating our question and answer session this afternoon. I'd like to ask you please to wait for the microphone and then give your name before you ask your question. Let's start here at headquarters. Administrator Griffin.
Thanks. That was very interesting. A long time ago in a galaxy far away, my PhD minor was in controls.
Oh, wonderful.
So I had some interest in all this. In recent years, there's been some work, I won't say off to the side, but not yet in the main line of control theory on genetic algorithms for getting to a desired outcome or an optimal outcome as measured by whatever objective function you want, starting with very simple inputs and allowing, for example, circuits to evolve with components to produce the desired result without a lot of human intervention. Have you thought about, it occurs to me that a way that a human being learns to fly is you're trying to make the airplane do what you want it to do, and you wiggle the controls around until you see outcomes that it's very like a genetic algorithm. You move controls until you see the result that you want, and your flight instructor is there to keep you from killing yourself. Have you thought about adapting some of the genetic algorithm work to adaptive control or intelligent control in the sense that you're doing it? You have a failure, you know where you want to be with the airplane, and let the controller experiment with itself to produce the desired outcome?
I'm glad you asked, because my PhD topic, I used genetic algorithms for control in 1988. So
I could have set you up for this question.
it almost looks like setup. Actually, my first entry into intelligent systems was via genetic algorithms. And what happened was we used genetic algorithms. I'll tell about my personal experience, and then I'll give you some more examples. What happened was genetic algorithms are intensive both from a computational point of view, but also information point of view. That is, if I have to explore the space, let's say 50 times, to do that in real time, using an airplane as for an example, I have to actually put the airplane into those situations. Now, to do that effectively, it'll be better if I can do it 5 times rather than 50 times from a population point of view. So I started looking at, from an evolutionary point of view, what other biological system does something like that. And a good example is the immune system. That's how I got into the immune system, because immune system is a very rapidly evolving systems. And we have used some of that for like fault identification. Now, in terms of using it in real time for unmanned systems, I think it's got a lot of potential, where you can actually explore your operating space. So it's a concept of exploration versus exploitation. I can use the evolutionary algorithms to explore the space, and for exploitation, I can go for actual control algorithms. We have done, you talked about the circuit evolution. Within my group, we have looked at using genetic algorithms even for design, for automated antenna design, for example. We actually flew one on an ST5. So it's got a lot of potential, and it's a good question. I think the only reason we haven't jumped fully into it because the manned systems constrain us to some extent.
Yeah, I probably wasn't as clear as I ought to have been. I wasn't thinking about putting the airplane through 50 different situations, but rather using a mathematical model of the airplane and put that through offline.
Yeah.
Essentially process that and then come up with the optimal control strategy for a given failure circumstance.
Yeah, that's a very good idea. I mean, we actually thought about using that.
Put the real airplane through those
which
situations.
You could if you have an unmanned system.
Yeah, but you could also crash it while you're doing it.
Yeah.
Yeah.
Definitely. I mean, I think exploration and exploitation, there's a big trade-off there. You have to be careful how you do it.
Anyway, interesting stuff. Thanks.
But they're using the model. I think that's a good idea. Definitely.
It's here at headquarters.
This is a pretty excellent talk, Krishna.
Thank you.
You are using neural networks to predict the future events. Suppose you had a lot of physics-based models. How would your approach change?
So that's a good question. I think physics-based models always is the first route to go. And one of the, I think, challenges is first getting the physics-based models. The other challenge is some of the physics models tend to be highly computationally intensive, like CFD modeling, for example. If we could conceptually do online CFD models and come up with stability and control derivatives, but we are not there yet, computation. And if we have an ability to do it, I would definitely use that and augment neural networks as a kind of a delta, a variation. So all of these architectures, you can easily make that as a retrofit in the sense a delta from what you know. You can always add to it. Can you use a hybrid system? Yes. I mean, we have talked about hybrid. In adaptive control, they call it either hybrid or composite adaptation, where you have some known systems and an unknown, and you can bring them together. And those are all architectures we are looking at. You are right, the architectures I showed did not say that, but yes, you can.
We have one more question here at headquarters. Doug Rohn.
Hi, Krishna. This is Doug Rohn. Are there any intelligent control systems that are flying in a commercial aircraft today?
As I defined it, no. As I have defined intelligent control, one could argue that there is a lot of built-in intelligence.
As you define them, what would be the when might we see them, or what are the the reasons that they aren't on today?
So let me correct myself by saying that there are deployed missiles. The JDAM missile is a good example, which is adaptive control, uses adaptive control. So there are flying vehicles that use it, but manned systems, there is none. So what is the constraint? I think constraint is verification and requirements. So there is a workshop coming up where we are trying to lay out requirements for certifying adaptive control. First, from NASA point of view, I mean, if we are going to put adaptive control on space systems, like maybe the next generation space vehicles, what are the requirements? So once we can lay out requirements from a NASA side, then maybe we can move on to the civilian side. But I think that's the key, is stating the requirements and then trying to make sure you meet the requirements.
Let's head up to Cleveland, Ohio for a question at NASA's Glenn Research Center. Glenn, go ahead. Glenn, can you hear us?
Hi, yes. What kind of work is being done for intelligent stall recovery?
Could you repeat the question, please? We only got about half of it.
Yes, my question was, what kind of work are you doing in terms of intelligent stall recovery? Yes.
Question about the work you're doing in terms of intelligent stall recovery.
Oh, intelligent stall recovery. That's so the philosophy has been to actually prevent stall rather than recovery from stall. So we are not specifically looking at stall recovery per se. Having said that, there are work done in the planning and the adaptive guidance aspects of it, where we are looking at trajectories for stall recovery. But all along if you look at adaptive control as a concept, the idea is not to get into stall. And most of the time, stall happens because stability is lost right at the beginning of an event and you get into a stall. So I don't know if I answered your question, but no specific intelligent control method is being pursued for stall recovery, but we are looking at guidance trajectories that will get us out of a stall recovery.
We have a question at NASA's Dryden Flight Research Center. Dryden, go ahead with your question.
Thanks for the presentation. This is Jonathan Pickerel at Dryden. You've already briefly mentioned this. So my question is, for flight control, is the future of flight control for adaptive and optimal control? Do you see a limitation in the current and in the future computing capability that we have on aircraft?
That is a good question. I don't think there is a shortage of computing capability. Some of these techniques I laid out are not that computationally intensive as we have implemented them. I think if you go if you compare, for example, real-time CFD modeling to what we do in intelligent control, orders of magnitude difference. Ours is not that computationally intensive. So that's one of the benefits. I don't think implementing them on current computers on airplanes is a problem. But if you do go to the advanced architectures like brain-like intelligent control and so on, I don't have an answer for that. But the current architectures that we are pursuing are not that computationally intensive. They are complex concepts, mathematically speaking, but implementation is not that hard.
All right, we're back here at headquarters for questions. We have one over here.
Hey, Krishna, nice talk. We often talk about technology having to buy its way on to actually be implemented. And what would you say you think is going to be the actual selling point for adaptive control, say, for the next generation of aircraft or beyond that? Is it going to be the safety aspect, or you hinted to some of the possible efficiency gains, or is it something else? I mean, obviously it'll be a combination, but what do you think is going to be the driving factor?
I think of safety as being something that's required that could drive intelligent control on next-gen vehicles. That is, if FAA dictated a level of safety that could be achieved very easily with adaptive control, then that will easily buy itself on an airplane. From an efficiency point of view, I think I know that Boeing Phantom Works has been trying to sell from an efficiency point of view for a while, and the tricky part there is they have not been able to actually flight test and document the advantages. This is one. I mean, we are in a very expensive business here. I mean, when we talk about showing ideas to work on an airplane, flight testing is a very expensive endeavor. So that's why they took the missile route, because it was cheaper, and they showed on a missile you can get very good performance for very cheap implementation. And not only that, missile to missile variations were easily accommodated. So I know that they are looking at cheaper ways to prove that this is very good for performance, and slowly the eyes are opening. But I think safety may be more of a faster way based on requirements to get into.
Are there other questions here at NASA headquarters? We do have one or two questions that have been mailed in to us. I'm interested in learning a little bit more about the impediments to adaptive control on production aircraft. You mentioned that computer capability might not be one of them. Are there others?
Right now, I think we don't understand the requirements. So when we have one of the challenging research that's being pursued simultaneously by many of our academic partners and by industry and by us is this idea of while you adapt, how can you quantify what the controller is doing? The data I showed about stability, the gain margin, phase margin is after adaptation. That we understand. But there is a fear going from non-adaptive to fully adaptive, the transition. What are the requirements for its behavior? It's when you think of intelligence, I think putting requirements is what is going to buy its way into any kind of deployed application. And what are those requirements? I think that's the unknown right now, and that's what we are pursuing. And we hope that once we have a set of requirements that are bounded, and then we can go and showcase that, then I think governing bodies like FAA will have to step in and fine-tune that and help us get on the aircraft.
And one other emailed question. You touched on this a bit in your talk about the role of intelligent flight control for space exploration. Can you expound on that a bit?
So the current applications that are deployed on, for example, the Mars landers, is the planning software. But from what I understand, all of that planning is done on Earth, mainly because the spacecraft still communicates with Earth for all its cycle. So the data comes back to Earth, and the planning software is used by humans on Earth to send commands back to the Mars lander. But the technology itself can work in real time if we can sense and act. There's been studies done, what they call a single instrument placement study at NASA Ames, where if you can sense and act without closing the loop with Earth, what kind of benefits you can get. And they've shown tremendous amount of benefits in terms of number of experiments you can do in a given day. And they've been pushed towards using real-time planning. So from the planning end, there's already research done and systems that are ready to go. From a control side, I think the one way we are trying to get control into space applications is via safety first. We are talking to the ARES project, talking about adaptive control as a way to implement a safer trajectory if needed. We are also trying to sell optimal, real-time optimal control as potentially for the future of spaceflight. So I would say currently, as far as I understand, intelligent flight control is not in any deployed space systems.
All right, thank you very much. That will conclude our briefing for today. For more information on the activities of the Aeronautics Research Mission Directorate and to view this talk a bit later on the web, go to our website www.aeronautics.nasa.gov. Thank you very much.